Hello and welcome back. Today we're talking about homomorphisms. So if I have a function called h, and it takes vectors from a vector space called v and changes them into output vectors in another vector space called w, and then in that case v would be the domain and w would be the codomain, then this is a specific kind of function called a homomorphism or a linear map if it abides by the following two conditions. The first is the preservation of vector addition, and this says that if I take two vectors in v, v1 and v2, and I add them together, and then I apply the function or the map to that result, that's the same thing as first applying the map to the vectors individually and then adding those two results together. I add two vectors in V and then I apply the map. It's the same thing as adding their two corresponding vectors, h of v1 and h of v2, which are vectors in W, the codomain, the output vector space, together. Similarly, we have the preservation of scalar multiplication. So if I have a scalar s and I multiply some vector v in the domain space by that scalar, and then I apply the map to it, that's the same thing as first taking h of v and then multiplying it by the scalar. You can see there's a nice correspondence between the vectors in v and the vectors in w if they're related by a homomorphism. We could say that linear maps preserve vector addition and scalar multiplication individually, or we could say this more concisely as a homomorphism preserves linear combinations from the input space in the output space. That is, h of some linear combination s1 v1 plus s2 v2, where we have these scalars s1 and s2, multiplying vectors v1 and v2, and then applying the map h to that. That's the same thing as taking s1 times h of v1 plus s2 times h of v2. The first thing that we did is we distributed the application of h to both of these vectors, s1 times v1 and s2 times v2, and then when we had h of s1 times v1 and h of s2 times v2, we effectively factored out s1 and s2 from both of those, and that's how we got these results here. So we preserve linear combinations in the sense that v1 maps to some vector in the codomain h of v1, which we might call w1, and v2 maps to some vector in the codomain h of v2, which we might call w2. And so if I take a linear combination of v1 and v2, and then I apply the map to that, the result I get is literally the same linear combination, but of w1 and w2. And this applies to any number of vectors. So if I took h of a linear combination with s1, s2, and s3 of v1, v2, and v3, for example, then I would get the same thing, the same linear combination of w1, w2, and w3, and so on. Here's an example of a homomorphism or a linear map. We have this function t, and it goes from R2 to R2, so notice the input space or domain can be the same as the output space or codomain, and it's defined by the following. It takes in a vector from R2, say xy, and it outputs another vector in R2, 2x, x minus y. Well, to verify that this is indeed a linear map, we'll show that it preserves addition, and then we'll show that it preserves scalar multiplication. To start with addition, let's say I'd like to evaluate this map for the input xy added to another input zw. So these are two different vectors in R2, and I'm going to add them together and evaluate that result. This is the same thing as evaluating the vector x plus z, y plus w, because I can just simplify this vector addition in the middle. And then if I actually apply the map to this, the result I get in a vector is 2 times the first component, which is 2 times the quantity x plus z, or 2x plus 2z, and what I get in the second component of my output vector is the first component of the vector that I input minus the second component of the vector that I input, x plus z minus the quantity y plus w, or minus y minus w. This result can be simplified to just 2x, x minus y, plus 2z, z minus w. And of course, the vectors 2x, x minus y, and 2z, z minus w are t applied to xy and t applied to zw respectively. And since I'm adding those, I'm adding t applied to each of these vectors individually. And so we can see that vector addition is preserved. I add two vectors in the input space in the domain, and then I apply the map to them, and that's the same thing as applying the map to the vectors first, and then adding those results now in the output space, now in the codomain. Now we can do scalar multiplication. Let's say I want to apply t to s, some scalar, times an input vector xy. Well, really s times this vector xy is the input, and so I can simplify this to t applied to the vector sx, sy. Well, now if I actually apply the map to that, the result I get is 2sx, sx minus sy in a vector. Now I can factor out s from this. That's s times the vector 2x, x minus y, but that's exactly s times t applied to the vector xy. And so we can see that when we multiplied this vector by the scalar s and then applied the map t to it, it was the same thing as first applying the map t to it and then multiplying it by the scalar s. So scalar multiplication and addition are both preserved, and therefore t is a linear map. So what we saw in that example is a kind of map that, in general, is going to be linear. So if I have a map t that goes from Rn to Rm, then if I apply this map to a vector from Rn, so there are n variables in this vector, x1 to xn, and that's equal to a vector with m many components, and each of those components is a linear combination of the n unknowns that we gave to it, then that is going to be a linear function or a linear map. Again, the output consists of m many linear combinations of the n many input variables. Again, another example of this might be some arbitrary map H that I've just come up with here. It's a map from R4 to R2, so the domain can be larger than the codomain. And say it takes this vector x, y, z, w to this vector in R2, 3x, z minus y. This is perfectly valid. Again, the two components of this vector in R2 in the codomain are both linear combinations of the components or the entries in our input vector. Another linear map that we have is the zero map. This one is pretty self-explanatory. It's usually just written as a zero, and it goes from, say, any vector space V to another vector space W. There's always a zero map between two vector spaces because it's as simple as saying that 0 applied to some vector V from the domain is equal to 0, the zero vector specifically in the codomain. So for example, if this were a map, the zero map from say R3 to R4, then if I input any vector in R3, the result that I would get would be the zero vector, but specifically it would be the zero vector in R4. So it would have 4 zeros like that. But what's important here is that it's the zero vector. I just wanted to specify that it's specifically in the codomain. You can verify the preservation of linear combinations on your own because this example is so simple. We also have the identity map, which might be written as a capital I. I like to write it as this sort of script lowercase I and d, and the identity map is also pretty simple. The identity map goes from a vector space, say v, always to itself, and when I evaluate the identity map for some vector v as the input, the result I get is just that vector that I input. The identity map outputs the input. This might come as a surprise to some viewers, but the derivative, which you learned about from calculus, is actually a linear map. Think about it. It's a function that acts on functions, and it behaves linearly, and I'll demonstrate this. Let's say we'll call this map d dx, and specifically, why don't we talk about the derivative map on, say, the space P2, which will be the space of quadratic polynomials, or second-degree polynomials. So these are of the form a plus bx plus c x squared. It takes in some quadratic polynomial, and it outputs the derivative of that, which will technically be included within the space of quadratic polynomials, even though you already know that the derivative of a quadratic polynomial is actually a linear polynomial. First, let's verify the preservation of addition. So let's say I'm applying this map d dx to the sum of two polynomials, a plus bx plus cx squared plus d plus ex plus fx squared. Well, the sum of these is going to be a plus d, that's the constant term, plus b plus e times x, that's the linear term, plus c plus f times x squared, that's the quadratic term. Now when I apply the map to this, the result that I get is, well, the constant term vanishes, the linear term just becomes a constant term, so the x goes away, and in the quadratic term, my exponent decrements from 2 to 1, so I just am left with an x, and the 2 multiplies out front. b plus e, now that's the constant term, plus 2 times c plus f times x, that's the linear term, and that's it. So you can see this is technically included within P2, but it's actually, at most, a linear polynomial, so this is really also in P1. Well, I can separate this out into b plus 2cx plus e plus 2fx. That's exactly the derivative of my first polynomial plus the derivative of my second polynomial. Of course, the verification for the preservation of scalar multiplication goes similarly, but I won't show it. Of course, not all maps are linear. Take this example. F of x is equal to x squared. So if I try to evaluate this for the sum of two inputs, x and y, the result that I'm going to get is x plus y quantity squared, which we know from the binomial theorem is equal to x plus 2xy plus y squared. What would the sum of this function applied to these two inputs look like? So if this were a linear map, f of x plus y should be the same thing as f of x plus f of y. Let's see if that's true. F of x is equal to x squared, and f of y is equal to y squared, which is not the same thing as x squared plus 2xy plus y squared. An example of why this isn't linear, and you'll run into a similar problem if you try to verify the preservation of scalar multiplication. Even this function, g of x is equal to x plus 1, which does graph a line on the coordinate plane, is not actually a linear map. If we test addition, for example, g of x plus y is equal to x plus y, our input, plus 1. However, if I take g of x and add that to g of y, the result that I get is x plus 1 plus y plus 1, which is not equal to x plus y plus 1. If this were a linear map, then these two things would be the same, and a similar problem arises for scalar multiplication. Now, if this function graphs a line, then how come it's not a linear map? The problem does not arise from this part. The x plus y is fine. That's just a linear combination of two of the inputs. It actually arises from this 1 here. If I think about what g of x equals x plus 1 looks like in space, it does not intersect the origin. Its y-intercept is 1. And this example brings up an important fact about linear maps. The zero vector in the domain V must be mapped to the zero vector in the codomain W. And of course, in the case of our previous example, g of 0 was equal to 1. I'll prove this statement in green simply by assuming linearity and then showing that, in fact, a function that does not abide by this rule could not be linear. So if g is linear, then it should be the case that g abides by the preservation of scalar multiplication. So if I multiply a vector by a scalar and then apply g to it, it should be the same thing as first applying g to that vector and then multiplying it by a scalar. So why don't I choose a special scalar? I'll say g of 0 times any vector in the domain, just any vector v, should then be equal to 0 times g applied to any vector in the domain. G applied to 0 times any vector of the domain is just g applied to the 0 vector. The other assumption we're making is that g does not take the 0 vector to the 0 vector, so it evaluates to something non-zero. So we'll just say that g of 0 is not equal to the 0 vector. In the case above, it was equal to 1. So that covers g of 0 times v. How about 0 times g of v? 0 times g of v is equal to 0 times some vector in the codomain that we get when we plug in v as our input. So let's call that w. In that case, this is equal to 0 times the vector w, but 0 times any vector, whether it's in the domain or the codomain, is just equal to the 0 vector. So when we try 0 times g of v, we do get the 0 vector, but when we try g of 0 times v, we do not get the 0 vector. By linearity, we should get the same thing. So this shows that if g does not take the 0 vector to the 0 vector, there's no way it could be linear. So this assumption runs into a contradiction, and there's the proof. And in proof writing, the contradiction symbol looks like this kind of hashtag that's rotated 45 degrees.